In a previous video, we have defined complex numbers and we've seen why they are so interesting, to model our physical world. Now, in this specific video, we're going to see some examples of how to use complex numbers, in particular in quantum physics, and why they are the perfect tools to mimic, some of the behaviors of quantum particles, and also help us solve some of the mysteries of quantum physics. So let's go.
The first example of why we use complex numbers, in particular in quantum physics, is a superposition of quantum states. In a previous video, about the Hermitian operators, we had this very important theorem, and this theorem told us that Hermitian operators are perfect to mimic the behavior of quantum states. Their eigenvalues are isomorphic to the values of the physical world, and any state can be expressed as a combination, or you can call it a superposition of their eigenvectors, And all of this only works because of the Hilbert space of state vectors, which is defined over C, the complex numbers. Now, the second example is a measurement order syndrome. In classical physics, the order with which you make measurements has no influence on the results. For instance, if you measure somebody's height and weight, you can first weigh her and then measure the height or vice versa. It doesn't matter. Well, in quantum physics, as usual, things are a little bit different. The order in which you make measurements often does have some influence on the results. We say that by stating AB is different from BA, or if you define C as being equal to AB minus BA, which is called a commutator here, well, quite often the commutator is not equal to 0. The commutator is a fundamental math object in quantum physics, because it determines whether two observables can be measured while in the same state. And this allows, for instance, to derive the Heisenberg uncertainty principle. Now, the A and B object that we talked about here, are operators, obviously, and they represent observables. And they are therefore Hermitian operators, as we've seen in previous videos. Now, an example for A and B would be, the position operator and the momentum operator. Hey, don't ask why it's called P. It's just the way it is called usually, so I use the same letter. It's easy to show that X is a Hermitian operator. But the momentum operator is a little bit more tricky. As you probably know, the momentum is based on the velocity, and it's a function of the position. So we could define it as, this operator here. But the problem is that we would find it's anti-Hermitian, which means it would be equal to minus its Hermitian conjugate. So what do we do to convert it to Hermitian operator? Well, it's easy, you just multiply it by I, and because the complex conjugate of I is minus I, that's it. So the real definition of P, of the momentum operator would be this, minus I times this constant here, d over dx. If you're asking yourself why, h is here just to make sure we have the right units, and the minus sign is here, let's say, to be consistent with Minkowski space in special relativity. It doesn't matter. But what's important here is that thanks to I, and therefore thanks to complex numbers, we can be isomorphic to what we actually measure in the physical world, and we can also derive Heisenberg uncertainty principle. Wow. Now, the third example is linked to the wave-particle paradox. Experiments showed that light, for example, could sometimes be interpreted as particles and sometimes as wave. And this guy, Schrödinger, he wanted to find equations to describe the quantum state changes over time, and that would follow wave propagation rules. Now, in classical physics, an operator called the Hamiltonian describes the movement of objects over time. In fact, it usually represents the energy of the object. That's what makes us move from one state to another state. And it's therefore a sum of kinetic plus potential energy. Now, Schrodinger's equations use a Hamiltonian too, to describe quantum particles' behavior. And they include complex numbers, like this. And the proof of this equation and their solutions will be in our next video. But just to give you a spoiler, these solutions are actually complex exponential, and which means they are periodic functions. Yeah, interesting, right? This one is an interesting example of why we need complex numbers. I found it in one of Leonard Susskind's books, which, by the way, I heartily recommend if you want to know more about quantum physics, basic principles, or physics in general. But anyway, I won't go into the spin definition, which is out of the scope of this video. Let's say it's just another quantum observable property with binary values. So the spin of a quantum object, in 3D space, there are observables. And these three observables, therefore, define three orthonormal bases, as we've seen before. So we can call it up-down, left-right, and front-back, for instance. Okay? Now, any spin state, as we've also seen before, can be expressed in one of those bases. For example, the front state is equal to alpha up state plus beta down state. And in fact, we know that the square of alpha, which is a complex number, is equal to the square of beta and is equal to 1/2. Because when you are in the front state, there is a 50% chance that your next measure in the vertical basis will be up and 50% will be down. And since alpha is equal to the inner product of F and up, in that case, because of this, we therefore have this equal to 1/2. And similarly, we have the same thing here, of course. So if we start from there, what we're going to do is we're going to make the assumption that the coordinates are complex, but we're going to check whether we only need the real parts, in which case we don't need complex numbers. So if we take the inner product of F by the up vector here, thanks to inner product's properties, you get this, and that is equal to that. And here we have the conjugates, because remember the inner product is the sum of the coefficient complex conjugate by the coefficient of the second vector. Therefore, if we multiply this complex number by this one, it's equal to that, and therefore equal to 1/2 because of this here. And of course, same thing here with beta. So now we have this and this, but we can do the same thing with state R, the right, and we'll assume that R is equal to gamma up plus delta down, and so we have this, and again we have something like that. And if we develop this here, like that, by definition of the inner product, well, then we get alpha star, gamma star is equal to 1/4, or a quarter. Same thing here. And therefore, this part here is equal to 0. Now, let's suppose, we're dealing with gamma and delta being real numbers, okay? Well, that implies, this implies that alpha star beta plus alpha beta star is equal to 0. Now, if we decompose alpha and beta, with their real part and imaginary part like this, and we develop that, then we get this. And therefore, alpha star beta is equal to this, plus this, plus this. And since we have this equation here, that implies that we have this result here. And that implies that either alpha is a pure imaginary number, therefore a complex number, or beta is, and maybe both. So the conclusion is, well, you can't escape imaginary parts, and so you need complex numbers, to define spin. So as a summary, the most fundamental equation in quantum physics, the Schrödinger equation, implies the use of complex numbers. The most fundamental quantum observable behavior, the spin behavior, implies the use of complex numbers. Complex exponentials are solutions of equations which describe the behavior of quantum particles. And we also saw that complex numbers are necessary to model the non-commutative order of measurements and explain Heisenberg's uncertainty principle. So now you really have, these are only a few yet fundamental examples of the use of complex numbers in quantum physics. But as you can see, they really help to find this isomorphism between mathematical world and physical world. Now, the conclusion, well, maybe they are not intuitive initially, but the use of these complex numbers really simplifies the modeling of quantum particles' behaviors.